Welcome to Ask and Learn.
So we're starting with two wires, one like this and another here, and they're given opposite charges, so I'll call this one positive Q and negative Q. Now they each have a radius r, and they're separated by a distance d. So first I'm going to want to find the potential difference because, well, we need the capacitance ultimately, and we're going to need to use the potential and the charge. So I'm going to want to integrate, I'll call this at the axis of the bottom wire 0. So I'm going to want to integrate from each surface. So I'll start at r, and I'll go to d minus r. So this is going to be potential at d minus r minus the potential at r. And then we're integrating from r to d minus r. Now, by definition, this is a negative for the potential. I'm going to integrate the field dot dr. So that's negative, but also since we have a field contribution from both wires, we need to double this. And so the left side of the equation, we just get delta V. And the right side, we have integral from r to d minus r. Now the field is going from positive to negative the way I drew it. So up to down, this is the field. And I'm integrating in this direction. So E dot dr is going to be negative E times dr because they're anti-parallel. So this actually turns into a positive on the outside, and we get E times dr. And this is going to be 2 times the integral of dr to d minus r of, and then the field for a wire is lambda over 2 pi epsilon naught. I'll call this r prime, so I guess this is r prime, just to make sure you know the difference between the r inside the integral and the r in the bounds. So we'll take the constant out, the 2's cancel. We get lambda over pi epsilon naught, and then we're going to integrate dr prime over r prime. So this is, we take the integral of basically 1 over r is the natural log of r from r to d minus r. So this is, let's see, so this is going to be ln d minus r minus ln r. And whenever we have the difference of logarithms, we can just take the quotient and put it inside. So this is going to be ln d minus r over r. Now, we're also given that we can assume d is much greater than r. So this minus r doesn't really make a difference. So this we can sort of approximate this, which will make it easier to deal with. So this is ln d over r, since the minus r isn't really going to change the numerator at all. So this is the potential difference, and now we know that the capacitance is the charge over the potential. So we can take Q divided by lambda over pi epsilon naught ln d over r. Now, lambda is just the charge per unit length. So this is going to be Q over L, and then the Q's will cancel out. All right, this is a lowercase l. So this equals L pi epsilon naught over ln d over r. And now if I really want the capacitance per unit length, so I can bring this into the denominator, and we get C over L is pi epsilon naught over the natural log of d over r. And that's exactly what we were looking for.